Okay, so let me start with maybe a 5-minute recap of what we discussed or what we are discussing. So we are discussing different ways of handling deadlocks. Specifically, we are now discussing deadlock avoidance, where the basic idea is as follows. The resource allocation state will be characterized as safe or unsafe. We have discussed what does safe or unsafe mean, but I'll just repeat. So assume that the current state is safe. Now so a state essentially means a state is defined by the number of available and allocated resources, maximum demands of the processes, and so on. Right? So assume that the current state is safe. One process asks for a resource. The question is whether the OS should immediately give this resource to the requesting process, or should the process be made to wait. Now, there are two situations, of course, that a process asks for a resource which is not currently available. Then the question even does not arise, the process has to wait. However, there may be some situations where a process asks for a resource that is available. Even then, the kernel does not allocate it right now. It asks the process to wait, because if this process were to be allocated right now, the state will become unsafe. Okay, so unsafe state basically means it may indicate a deadlock. It's not a guarantee, but an unsafe state may lead to a deadlock. So that is what the kernel tries to avoid according to deadlock avoidance. Right? So it's trying to even avoid an unsafe state which may lead to a deadlock. So then we actually define what safe state and unsafe state is. So a system is in a safe state if there exists a sequence of all processes in the system such that for each PI, the resources that PI can still request can be satisfied by currently available resources plus resources held by all Pj with j less than I. Okay. So basically, suppose there are three processes P0, P1, P2. The state is safe if, let's say, P0 has got all its necessary resources. So at some point it will complete. Then it will release some resources after P0 completes. Using those resources, P1 can complete. So eventually P1 will complete and it will release further resources. Using all those resources freed by P0 and P1, P2 can complete. So if there is some sequence like this, then the state is safe. And such a sequence is called a safe sequence. Okay. Now we had a discussion yesterday. So I mean, those who did not attend the compensatory class yesterday should see the recording. We understood that, say at the current moment, no resource is free. Every instance of every resource is allocated to some process, and processes are demanding for more. Even under all these situations, the current state may be safe. That means the current state may not lead to a deadlock because such a safe sequence exists. Okay. Right. And also, so definitely a state is unsafe if it is not safe. That means if there is no such safe sequence. However, unsafe state does not necessarily lead to a deadlock, but it can lead to a deadlock. Right. So, okay, Pankaj, can you give an example where an unsafe state may still not lead to a deadlock? Okay, first of all, understand that in this algorithm, which we will discuss now, unsafe state is also avoided. Right, so the algorithm is specifically meant to not allow the system to go into an unsafe state. So your question is a very valid one, but understand that this question does not actually apply to the algorithm which we are going to discuss, because it is not that it is taking a chance on going into an unsafe state. It may or may not lead to a deadlock. So that's one point. But then your question is valid that there can be unsafe states which may not lead to a deadlock. Okay, this I am unable to think right on top from my head because you need a concrete example, I guess, to answer this question, right? So, it will take time to create such an example and say now. right? So I'm not trying to answer this question right now, but yeah, I would encourage you all to think about states which are unsafe. First of all, let us go ahead and understand the algorithm which we are going to discuss. But then I would leave it to you to figure out an unsafe state which may not lead to a deadlock. Maybe you should try with a very simple. No, that's the thing. I mean, if you try with a very simple setting, like only two processes, then it may be possible that an unsafe state will always lead to a deadlock because, yeah, so you have only P0 and P1. So, yeah, I mean, yeah, so from the top of my head, I'm not able to figure out an example right now. So possibly you have to try it out with several several processes. Or yeah, okay. So I'm not trying to answer that question right now, but okay, Sriharsh has a suggestion. Safe, unsafe is defined by maximum number that a process may need. So if process have a high maximum but use less resources, it might be unsafe and there would be no deadlock. Sure. That okay. Maybe a process has given a conservative estimate of the maximum number of resources it needs, but then it does not need all those resources which it declared earlier. So then the deadlock might not arise. Possible. Okay. But yeah, I guess, I mean, Pankaj meant that all the resources would be used. At that point, I'm not sure if that's the idea, but yeah, the answer by Sriharsh is actually good because again, let's go through the algorithm, then maybe things would be clear. But there is a concept of the process actually declaring upfront how many maximum resources it would need. So ultimately, if it does not need all those resources, then even if the state becomes unsafe, the deadlock may be avoided. So yeah, I believe that the answer by Sriharsh is good, but let me actually go to the algorithm. Then these discussions may make more sense, especially because not everyone attended yesterday's compensatory class. Okay, we discussed an example, but this I can just, when I share these slides today, you can check it out. Okay, now let us discuss this algorithm, which actually can be used to figure out if a state is safe or not. So these are the assumptions of the algorithm. It assumes that there are multiple instances of each resource type. And this is what I was talking about. Each process must declare the maximum resource requirement a priori. Okay. Now, when a process requests for a resource, it may be immediately granted the resource, or the OS might actually ask it to wait, even if the resource is available. This is because the system wants to avoid an unsafe state. So let's see. First of all, here are some data structures which are used by the Banker's algorithm. Okay, the algorithm looks complicated, but actually it's quite simple. Okay, if it does not look complicated to you, then great. But yeah, to some it might seem complicated, but actually it's quite simple. Okay, so it uses these vectors like available. So it's a vector of length m, where m is the number of resource types, right? So if so this vector essentially stores how many instances of which resource are available. Okay. This is max. This is what is declared by the processors upfront. That is, what is the maximum number of what is the maximum number of resources that a process is likely to ask for. So this is actually a 2D matrix, n cross m matrix, because every process Pi needs to say how many instances of which resource it will use. So basically the ith row of this matrix is the maximum resource demand of process Pi. Okay, the ith row of this matrix is the maximum possible resource demand of Pi. Similarly, this is the allocation matrix which characterizes the current allocation. So the ith row of this matrix is what resources have been allocated to process Pi. Right. So if allocation ij equal to k, that means that Pi has been allocated currently k instances of resource type Rj. And finally, you have the need matrix, which is basically max minus allocation. That means how many further instances of a resource type can PI still ask for? That is stored in the ith row of this need matrix. Okay. Okay. So before we actually go to the algorithm, any questions? Or okay, let me actually discuss the algorithm, then I can ask for questions. So this Banker's algorithm actually has two algorithms within it. This algorithm which we are discussing now is called the safety algorithm. This is for finding out whether the current state is safe. So this is how it proceeds. I think it's simple. Just let me explain a bits and pieces. So basically it goes ahead with this vector work, which is initialized to available, and finish, it's initialized to whether a process has finished or not. Right, so finish I equal to false, because at present assume that all the processes are running. Now this step 2, find an I such that both of these conditions hold. Finish I equal to false and need I less than equal to work. So now let me ask you, how do you semantically explain this step 2? What is going on here? Find an I such that these two conditions hold. What is semantically going on in step 2? Yes. So okay. Yeah, okay. So I think yes, Shaumitro, Shrihas, Dhrumil, Pankaj all have given the correct answer, that basically it's trying to find a process which is still running but which can complete. That means the further resources that it needs are available already. Right. So yeah, so suppose this kind of a process exists, then it's at least one process can end. And then, okay, what is this step 3 doing? Or okay, let me ask, what are step 3 and 4 doing? Yes, so what Shomitra says in step 3 is the system is kind of assuming that, let's say this process I, which we found in step 2, completes. Note carefully, it has not yet completed actually. Okay. However, the system, so again, understand what this whole algorithm is trying to do. It is trying to figure out whether a state is safe, whether the current state is safe. So basically, it is trying to figure out if there exists a safe sequence. So for that, it has to find at least one process which can complete with the available resources. So for that, it tries to find out in step 2. If no such process exists, then of course this state is unsafe. So yeah. Right. So again, see, so if no such I exists, go to step 4. So then what is happening in step 4? If finish I equal to true for all I, then the system is in a safe state, otherwise state is unsafe. That means what? If at some point in this algorithm you see that no such I exists, but there are some processes which would not get over by this time, then the state is unsafe. Basically, there does not exist any safe sequence. Okay. But assuming that such an I exists, then in this step 3, what is happening is the system is assuming that, let's say this process which we found in step 2, this will end at certain point of time. Then can I find another process which can complete using what is available right now and what would be released by this process which terminated, let's say, which would terminate. Right, this is a hypothetical scenario. The process found here The process found in step 2 has not yet terminated because you see finish I equal to false. However, the system is assuming that some point it will terminate. Then can I find another process which can also terminate? Then can I find another process which will also terminate and so on. So basically it's trying to find a safe sequence. Okay, any questions about this algorithm? Okay, Shubham is asking if a safe sequence exists, is it always guaranteed that this algo will find it? Okay. I cannot say that I know the proof, etc. But then I cannot think of a situation where a safe sequence exists, but this algorithm is not able to find it. Though I do not know of formal proofs. For that, maybe you'll have to look up the paper which actually proposed this Banker's algorithm. But I guess that this algorithm is guaranteed to find a safe sequence if it exists. Of course, if any of you can think of a contrary situation, then I would like to know also. Any other questions? Okay, if not, let me proceed. So now let me ask a small question that, so this is the safety algorithm which decides if the current state is safe. Now Banker's algorithm actually has another algorithm. Can any of you guess what that second algorithm is for? One key step we have not defined what to do. Can any of you think? No, okay, Pankaj, no. So the Banker's algorithm assumes that the set of processes is what we have now. So a new process is not considered even. Order of the processes. Order of the processes. No, see, I mean the Banker's algorithm cannot decide order of processes. That happens like scheduling, which we have discussed in detail. So like if Banker's algorithm tries to fix the order of processes, then there will be a problem. Okay, Ayud and Shomitra, I'm not able to understand your answers. Need changes means switching to another state. Okay, think a bit. Think of the bigger picture. What are we trying to do? Okay, Ramnivash has an observation that we haven't used the max matrix yet. Completely true. So then there should be some other algorithm, right? So can you think what that would be for? Think of the bigger picture. We have not defined one key step. Exactly what she has said. See, this algorithm which we just discussed is to ascertain whether this current state is safe. But then what we are actually looking for is a process has asked for a resource, whether we should allocate it right now or whether we should make it wait. That is not answered in this algorithm. Okay, so that is why we need another algorithm, which will use the max matrix also. But yes, that is why we need the second algorithm. I hope it is clear. But this algorithm does not actually say whether a requested resource should be allocated right now. So therefore, let us go to this next algorithm. This is the resource request algorithm for process PI, which determines whether a resource request can be safely granted. So basically, remember these things we have discussed earlier, that request I is the request vector for process PI. So this, the kth element of this vector says how many instances of resource Rj, sorry, the jth element of this vector says how many instances of resource Rj PI can still ask for, right? So first of all, this is just a check that if request I less than equal to need I. If this is not true, then the process is violating its max condition. Remember, need is max minus allocated. Okay, let me just go back to that slide. Yeah, see, need is basically max minus allocation. So now, so need is how many more instances of a process can PI ask for at most. So now if we see that request I is greater than need I, then that means the process is violating its own declaration. So it's an error condition. Okay, otherwise, see again. Next step is if request I less than equal to available. Okay, then go to step 3. So if this is not true, what does it mean? That process I is asking for a resource which is not available. So of course, PI has to wait. There is no decision that needs to be taken. Okay. So these two are the simpler best cases. I hope it's clear. But now this is the main step, step 3. So here again, see, PI has not yet ended. However, sorry, PI has requested a resource. It has not been allocated yet. In fact, that is exactly what the kernel is trying to decide, whether the process should be allocated to resource should be allocated to PI or not. However, it pretends that it allocates the resources to PI and then checks if the resulting state is safe. Okay. So first of all, how to pretend that resources are allocated to PI? By these steps. See these steps and tell me if you don't understand. So this is a pretension that the system pretends that it allocates the resources requested by PI. So it pretends that the resources are allocated to PI and then checks if the resulting state is safe. How can it check if the resulting state is safe? Yeah, okay. Pankaj, I'll come to your question. But yes, the question that I asked, like Shubham, Ayush, you have answered. So the algorithm that we discussed in the previous slide, that can be used to check if the resulting state is safe. See, after all, that algorithm which we discussed previously, that given any state, it will check it is safe. So when discussing that algorithm, we said that we are checking if the current state is safe. But then the same algorithm can be used to check if a hypothetical state is safe. Now we are talking about hypothetical state, that let's pretend that the resources requested by PI are allocated. So then we will reach a hypothetical state. Let's see if that is safe. So the same algorithm as we discussed previously can be used. Okay. So if that state is safe, the PI's request is immediately granted. If not, if that safety algorithm says that the resultant hypothetical state would be unsafe, then PI is made to wait. Okay, Pankaj, yes, of course. I mean, you assume that you allocate these resources to PI, which it has requested currently. But you cannot assume that PI will end. PI may need more resources. So its need I vector, no one says that need I has become 0. Sure, need I can become 0, but then you cannot assume it generally. Pi may even require more resources later, right? So any other question about either of these two algorithms? Okay, Shubham has a question. Can we say that the banker's algo is actually doing BFS through a graph of states? Okay. I did not quite understand how that question came up. So Shubham, maybe you can unmute yourself and just say what you have in mind.
I mean, I was asking that it is like you are from the current state, which states you can reach. You are actually trying to, like trying to brute force your way through it. Like, if this state works, I will go to there and mark it as safe. So it is like a BFS kind of approach, right?
See, I am not fully agreeing to this because first of all, it's the states are not defined. I mean, Banker's algorithm cannot make assumptions that in what order different processes will request resources. And based on that order, the states will change. So this graph you are talking about, this graph does not exist, or this graph is not deterministic. At least Banker's algorithm does not have any way of figuring out this graph. It will completely depend upon which process asks for which resource when. So I possibly understand what you are trying to imply, but I would not agree with that. Of course, if you have anything more to say, just maybe Shubham, you can unmute yourself and tell again. But this graph, I believe that this graph itself is not defined, or it cannot be even deterministically defined. Therefore, like doing BFS, I don't know. I don't think so. And
Okay.
besides, why is the concept of even BFS coming? Because uh, this is not trying to explore multiple hypothetical states. This is trying to just identify one hypothetical state and whether it is safe or not. So I don't think anything like BFS is going on where, like, even if this graph could have been defined, you are checking all neighbors of this state. I don't think that is happening. Or, I mean, I don't think that analogy is, at least I'm not able to understand it. Okay. Okay, Shomitra is asking, is it a type of topological sort? Well, sure, the safe sequence can be linked to topological sort, because after all, topological sort also may give tries to find some kind of ordering. So, and the safe sequence also, especially if not this, at least the safety algorithm, which we discussed in the previous slide, that can be linked to topological sort probably. Because after all, it is trying to figure out an ordering of the processes which is safe. I mean, a sequence of the processes which is safe. So yeah, I mean, it can be linked to topological sort. Okay, any other questions? Okay, but see again, I'm not quite convinced with that way of thinking of this as a graph of states and then doing either BFS or DFS, etc. So I mean, if any of you want to tell that, I would like to hear, but I am not very much convinced about that graph of states because Banker's algorithm cannot determine that graph because it does not know in which sequence processors will ask for resources. Sure, someone might say that you do a brute force kind of thing, like consider all possible states, but that would be huge and that's an impractical approach. Any other questions? Okay, if not, let's proceed. Okay, here's an example. I'll quickly go through it, but again, the slides will be available so you can spend more time. So assume that there are these 5 processes, P0 through P4, and we have 3 resources types with the instances given. And let's say at time T0, this is the snapshot. So this is saying how many processes are allocated, how many resource instances are allocated to which process. I'm not spending too much time on this example because I want to finish this topic today, and I mean the slides will be available, so go through it. Yeah. So now so basically from this max and allocation, we can define need matrix. So now as you see, the ith row tells, or this row tells what more resources P1 can ask for. So P1 can, apart from what is allocated right now, right? Okay, let me go back to the previous slide. This is allocation. So this row says what P1 has been allocated right now. And this row says what is the maximum possible number of resources that P1 can ask for. So this row minus this row will say what are the resources that P1 can still ask for even after this, after point T0. That is what is here. Okay. Now again, go through it, work out the example. You will see that this system is in a safe state since this sequence is a safe sequence. P1 can finish first and so on. So when we will get the slides after today's class, go through this. Now, so let's say that P1 requests this instances. So resource type A, it asks for one instance. It does not ask for any instance of resource type B, and for resource type C, it asks for 2 instances. Okay. So first of all, first check is that request less than equal to available, and that is true. So that means, see, if this was false, then P1 would of course have to wait. So then the algorithm need not be even run, let's say. However, this is, say in this case, request is less than equal to available. So if the kernel wants, it can allocate all the resources to P1 right now. But should it? See, this is the state after trial allocation to P1. Focus on this trial allocation. This is not yet done. This allocation is not yet done. The system does this trial allocation or pretends that it allocates and then gets this state. Now it checks whether the state is safe. And yes, if you again work out this example, I leave it as a task, you will see that still a safe sequence exists. And therefore it can be granted. Okay. And then there are other couple of questions. So these I leave for you to figure out. You can see the book. Also, you can try to work out this for yourself. You'll see that maybe some of these requests cannot be granted right now. Okay. Okay, so this was our discussion on deadlock avoidance, where we specifically studied the Banker's algorithm. Any question at this point? Okay, if not, then let's proceed. Okay, I have a question. If safe sequence is P1, P2, P3, P4, but currently satisfying the request of P1 will lead to an unsafe state, then what is done? Sorry, okay, Pankaj, I'm not able to understand the question. Can you unmute yourself?
Yes, sir. So, sir, if a safe sequence, suppose there are 4 processes, so if save sequence is P1, P2, P3, P4, just for convenience. But current request of P1 will, when if we satisfy that and we check the save sequence again, then we do not find any.
Yeah, so when
Yes.
you say the P1, P2, P3, P4 is a safe sequence, you mean at the current point it is a safe sequence.
Yes, sir.
But
For convenience, I took it in that order. Yeah, after that
yeah, that's
the
okay.
order may change.
But after, suppose the resource allocation is done to P1, then the state would not be safe.
Yeah.
So then there would be no unsafe, no safe sequence.
There is no safe sequence, correct.
Then of course P1 cannot be granted those resources.
P1
right
cannot be granted, but then
Hmm.
for whom are we waiting? Because according to safe sequence, P1 is the one which is supposed to complete, supposed to like proceed first, right?
Okay,
because that is
that's
the
a
safe
good
sequence.
point. See, again, that's a good point. The safe sequence possibly starts with P1, but that does not mean that P1 has to be the one which has to end first. Again, going back, maybe some other process may not require all the resources that it thought it would need. Maybe that process can end early and remove, and release some resources.
So if some other process will request, we may
Or at
allocate
least
it
see, even if at the other processes P2, P3, P4, maybe they do not end, but they release some resources. That can always happen, right?
Yes, sir.
So then maybe P1 can be granted.
So we will be waiting until some other, like something else happens.
Process
And,
releases resources, yes.
yeah, okay. Okay, thank you.
Okay, that's a good point. The safe sequence starts with P1 does not necessarily mean that P1 has to be the first process to end. That's one point. Some other process P2, P3, P4 may decide that it does not need any more resources and it may end. Second, it is not necessary for a process to end. So suppose, let's say that's a good example that Pankaj gave. Suppose current state is safe and the safe sequence starts with P1. So then we think that P1, at least say, let's say P1 is the only resource, sorry, P1 is the only process which can currently end. Right? So yeah, and yeah, so okay, I'm coming to Shaumitra's question. So let's say P1 is the, okay, since Shaumitra's question is also very much related, then let's take that also in. But suppose if no process releases any resource until they complete, okay. Okay, first of all, let me think for a minute. Yeah, okay, so let me think. Okay, see, Pankaj, you said that P1, P2, P3, P4 is the safe sequence, which starts with P1. So what does that mean? Should P1, will P1 ask for any further resources? Let's go back once to that slide, which was defining safe sequence. Yeah. So yeah, if the safe sequence starts with P1, that means that P1 can be satisfied by currently available resources plus resources held by P1. So then if your safe sequence starts with P1, P1 should not request for any, okay, no, wait. Yeah, so see, if your safe sequence starts with P1 according to your question, then I think this situation cannot arise that P1 is asking for resources which will lead to a safe state, unsafe state, sorry. Think about it. Tell me if what I'm saying is not correct. But I believe from this definition, if you say that your safe sequence starts with P1, yes, Pankaj, unmute.
Sir, then near a few slides further, can you go
Further which way?
down? I mean the further slides near the part where we stopped before the discussion, just before that example.
This one?
Even fine. The next one. Yeah, here in this one. So basically in this case also we are doing the same thing, right? We just now about this before the examples. 36, slide 36.
36, yes.
I think it is slow to update. Yeah, now it's visible. So in here we said need I if it is satisfied, then according to the previous algorithm on 35, we are sure that I will get completed. And now we are saying that if request I is satisfied, it may happen that we are checking again that it will lead to a safe state or not. Then here also it is already given that every time, even if request I is satisfied, it will always go to a safe state, right? It is same as what I just asked. So why is there a need for the second algorithm then?
Wait. Sorry. Okay. Can you repeat the question? I kind of got confused.
In 35, we just now determined that PI is the first one in this sequence, correct?
Yes.
So now in this 36, we are saying that if PI is requesting RI, or some request I, then it may so happen that if we allocate request I, it may still go to unsafe state. And that's why we need to check and determine that if we
First of
allocate
all,
or not.
Okay. I think you are making one slightly wrong assumption. It's not necessary that every time this algorithm, which you see now, is run, it's not necessary that immediately before this, the algorithm in the safety algorithm will be run. So this algorithm does not say at first run the safety algorithm. Safety algorithm is run here only. Right. So actually, see again, okay, this is possibly a good confusion because it can happen to everyone. It's not that the safety algorithm which we discussed. It's not that at some random points the kernel will try to execute this algorithm. Let's see if the state is safe. No. Remember, all these are overheads. So actually the safety algorithm is not run independently, possibly never. When a request comes from a process, then this algorithm runs, the resource request algorithm. As a part of that, the safety algorithm is run.
Yes, sir. So if safety algorithm is run, then resource request algorithm is useless, right? Because safety algorithm will tell us that if PI is the first process in our safety sequence or not. And if it is, then satisfying its request will always leave a safe sequence anyway.
Okay, so see, so then let's think in practice what we will do. So let's say P1 has requested for some resource. What do you want to do? You want to run this algorithm or the safety algorithm?
I want to run safety algorithm, and I think this one will not be needed then.
Okay, then why do you want to run safety algorithm?
Because if
just to check if P1 is the first state in the safe sequence, first process in the safe sequence.
Yes.
Isn't that taking a blind risk? As in, who knows if it will be the first process in the safe sequence? Then you will anyway have to run this algorithm. If not, then why should we not start with this algorithm itself?
I mean, like just now I said that first algorithm is run as a part of this one only, right? Just before this anyway.
Yeah, it will run here. So the system will pretend that it allocates the resources to P1 and then run the safety algorithm.
And then like now you're saying that we run this one before that, so it's like kind of contradicting. Like one of them should go first. If one of them is running, then other one is not needed.
That's what I'm saying. Right? See, algorithm, these algorithms are run when a process asks for a resource. I'm saying this is the algorithm which is run. As part of this, the safety algorithm may be run. But you are saying that you want to run the safety algorithm first to determine if the process just requested a resource is the first process in the safe sequence. I'm saying that's a waste of effort.
Achha, okay, got it.
Okay.
Thank you.
Okay, fine, thanks. Okay, Soumitra, yeah, it's possible. There can be many safe sequences, yes. There can be many safe sequences. Sure. Yeah, okay. So I think, okay, I can understand this is a common confusion because this FT algorithm was discussed first and then this. But then understand that in practice, the running order would be different. When a request comes from a resource, this algorithm will run. And as part of this, the safety algorithm will run. Okay, that's a good point. Actually, I mean, the practical order of running the algorithms is reversed from what we discussed. Okay, in the interest of time, let me move ahead because I want to complete this. There's not much remaining. So yeah, okay, so this was about deadlock avoidance. So till now, whatever we have discussed, it has been that we want to avoid getting into a deadlock situation. In fact, we want to avoid getting into an unsafe situation and all. But there is this other family of processes which says that okay, if a deadlock may happen, but let's try to detect a deadlock and then recover from it. So let us there is not much technical meat here. Let me just go through. So basically what this does is periodically run deadlock detection algorithm. If deadlock detected, then you have to recover, right? These algorithms can be quite complicated. Let us discuss a very simple algorithm which assumes a single instance of each resource type. So this is actually very simple. In fact, in the previous class, some of you were pointing to it out also. We will maintain a graph which is a wait for graph. So here the nodes are processes and there is an arrow from or a directed link from PI to PJ if PI is waiting for PJ. What does PI waiting for PJ mean? So PI has requested some resource which is currently allocated to PJ. Therefore, PI is waiting for PJ to release that resource. Okay. Now, I guess many of you have already understood that this graph can be derived from the resource allocation graph. This is just an example, right? So see here, P1 has requested, P1 has requested for an instance of resource R1. Here we are assuming there is only one instance per resource, but that resource R1 is allocated to P2. Therefore, P1 is waiting for P2 and you have this edge from P1 to P2. Okay, so it's I think you understand that it is very simple to derive the wait for graph from the resource allocation graph. Okay, so now let me ask, what do you think will indicate a deadlock? A very simple question. What do you think will indicate a deadlock? Now that we have created this wait for graph? Yeah, a cycle in this wait for graph will indicate a deadlock. Okay, so yeah. So basically, what you have to do, periodically invoke an algorithm that searches for a cycle in the wait for graph. If there is a cycle, there is a deadlock. So it's plain and simple. However, the cost is here that a cycle detection algorithm on a graph requires order n square operations, and n can be quite huge. There can be thousands of processes running in a system. Therefore, this is very inefficient to run this kind of an algorithm periodically. Remember, you have to do this periodically. Also, we took a very simple assumption that only one instance per resource type. If actually there are multiple instances of per resource type, then there are algorithms, but they are likely they are understandably more complex with higher time complexity. So see, again, remember what we discussed once, that actually in a practical operating system, often nothing is done to detect deadlocks. And this is, you are getting the reasons why. There are algorithms, however, they are quite costly. Okay. Also, suppose that you run such an algorithm. You say, okay, I'm willing to pay the cost. I will run such an algorithm. Okay. And then you discover that there is a deadlock. Then what you need to do? You want to recover from it. So then there are two broad approaches. See, the next few slides do not contain any technical stuff. I'll just skim through. But one thing I would ask you to notice, why is nothing done in practice to detect deadlocks? The reasons you will find in every step. First of all, you understood that even a very simple algorithm requires order n square, where n is the number of processes. That's costly. Besides, even if you do that, let's see what's the difficulties next. So you have to recover from a deadlock. So basically, there are two approaches for recovering from the deadlock. Either you have to terminate one process, at least one, or you will have to preempt some resources from some process. The question is which process? because that whichever process you choose, it will be unfair to that process. Right? Because maybe 8 processes are locked in a deadlock. You say I'll choose the U. That will be unfair. So let's see the approaches. First approach, process termination. So okay, one simple idea is about all deadlock processes. But I guess you understand, extremely bad solution. So next, about one process at a time until the deadlock cycle is eliminated. But then which is that process which you will choose to abort first? Whichever you choose, it might become a bit unfair. Well, people have given different ideas, like there can be priority of processes. Then there can be how long the process has already computed, etc. How much resources that process is holding, whether it's an interactive process or batch process. If it is an interactive process, maybe you should not kill it. But if it is a batch process, then maybe you should, okay, it's relatively less. But yeah, you can understand it gets into muddy waters, like how to choose which process to abort. Similar case, this is resource preemption. So basically you are trying to resolve a deadlock by forcing some process to give up some resources. Right? You preempt some resources. So then again, there are two things. One, you have to select a victim. That means from which process to preempt resources. That's again complicated. It may be unfair. Besides, the next point is extremely important. Suppose you preempt some resources from a process. Let's say it was an read-only file which you preempted, or something read-write file which you preempted. That means what? But this process needs to complete later. So it may well be that it had already written some elements to that file. So now it will be an inconsistent state if you simply take that file away. So you'll have to do what is called a rollback. You may have come across this term in a database course also, like rollback of a transaction. So basically the selected process has to be returned to some previously known safe state and then restarted. So basically you understand that all these can be done, but these are extremely difficult to implement in practice. High time complexity of detection of deadlock. Even after you detect a deadlock, which process to abort or preempt resources from, that's a problem. A process may have to be rolled back. All these are problems. And that is precisely why most operating systems follow this algorithm called the ostrich algorithm. So I don't know if you know, this is a common saying with ostriches. Don't ask me if it is true, that when an ostrich sees danger around, it does something foolish. It simply buries its head in sand and pretends that the danger will pass. I really cannot vouch for whether an ostrich really does that. I doubt. An ostrich should not be so stupid. But then that is, maybe it does, I don't know. So then, yeah, that is what most operating systems do. They just pretend that there is no problem. Anyway, deadlocks occur very rarely. And also, importantly, the cost for prevention or detection is very high. And at least say Unix or Windows takes this approach. Okay, that's it. So this is a summary of what we discussed in deadlocks. I see that we are already past the time. Still, I can wait for a couple of minutes to hear any questions. But if you don't have any questions, feel free to leave. Okay, then thanks everyone. Does not seem to be any questions. I'll put up these slides today. Thanks everyone. Okay, so a couple of announcements. Sorry. One thing is, yes, tomorrow I would not be taking the live class. So that's why I took the compensatory class yesterday. Also, but okay, remember the lab things. So one thing is there is no live lab session today because the deadline is 11th. next Thursday. However, for assignment 4, you need to fix up a time with the TAs and get your assignment 4 graded. And this you have to do in the next 4 days. Okay. And of course, work on assignment 5, which you will have to submit on Thursday. Next Thursday, I mean. Fine. Thank you, everyone.